around 500 years before Christ, on a boat somewhere in the Mediterranean, a man was thrown into the sea and left to drown. He was not a criminal. He was not a traitor. He was a mathematician, and his crime was discovering a number. That probably sounds like an exaggeration. It is not. The man's name was Hippasus of Metapontum, and he was a member of the Pythagorean brotherhood, a secretive religious order in southern Italy that believed with the fervor of absolute conviction that reality was built from whole numbers and the ratios between them. 1 is the point, 2 is the line, 3 is the surface, 4 is the solid. The ratios between these numbers produce the musical harmonics that govern the cosmos. The Pythagoreans had a word for this. They said, all is number. And they meant it literally. Numbers were not tools for describing reality. Numbers were reality. Every star, every stone, every vibration of a lyre string was a ratio of whole numbers. And the universe was, at bottom, perfectly rational. Then Hippasus found something that did not fit. He took the simplest geometric object imaginable, a square with sides of length 1, and he measured its diagonal. By the Pythagorean theorem, their own theorem, the diagonal should have a length equal to the square root of 2. And Hippasus proved, with a few lines of airtight logic, that this number cannot be expressed as a ratio of any two whole numbers, not because we have not found the right ratio yet, not because the calculation is difficult, but because no such ratio exists. The proof is a logical impossibility. The diagonal of a perfect square is a number that the Pythagorean universe has no room for. What nobody knew at the time was that this single number, this seemingly small anomaly in an otherwise elegant system, was the first crack in a foundation that has been crumbling for 2,500 years, and it is still crumbling today. The Greeks had a word for what Hippasus found. They called it allegos, and that word carried a double meaning that I personally think is one of the most poetic accidents in the history of language. Logos in Greek means both ratio and word, so allegos meant simultaneously without ratio and without words. Unspeakable. The number could not be expressed, and it could not even be named in the Pythagorean framework. It existed, the geometry demanded it, but their language had no place for it. The modern English word irrational comes from the same root, and it carries the same double meaning we have mostly forgotten. We use irrational to mean crazy, illogical, but the original sense was closer to inexpressible. Something that is real, but cannot be captured in the terms we have built to describe reality. In Latin, allogos became surdus, meaning deaf or mute, which is where the English mathematical term surd comes from. A deaf number, a mute number, a number that cannot speak. According to Iamblichus, writing in his On the Pythagorean Life around 300 CE, Hippasus perished at sea for his impiety. Other ancient sources say an unnamed Pythagorean who revealed the secret of incommensurable magnitudes was expelled from the brotherhood and had a tombstone erected in his name, as though he were already dead. Pappus of Alexandria, writing around 320 CE, tells a similar story without naming anyone. Now, I should be honest with you, because I think the audience for this channel respects honesty more than drama. These sources were written between 500 and 700 years after the events they describe. Iamblichus himself gives 5 contradictory accounts of what happened to Hippasus. In one section, he says Hippasus was drowned by divine punishment for revealing the construction of the dodecahedron. In another, he says an unnamed man was expelled for revealing the nature of rational and irrational ratios. In yet another, the same unnamed man drowned at sea. He cannot even keep straight whether Hippasus belonged to the mathematikoi or the acousmatikoi, the two factions within the Pythagorean community. The dramatic version you have probably heard, where the Pythagoreans physically threw Hippasus overboard during a sea voyage, appears in popular books by Simon Singh and Maurice Klein, but it has no basis in any ancient text. Singh even places Pythagoras himself at the scene, which is impossible since Hippasus lived more than a century after Pythagoras died. Peter Gainsford, a classicist who has written extensively about this legend, summarizes it well. Hippasus was not executed or thrown off a ship. He died in a shipwreck, and some moralists attributed this to divine agency. But even this honest summary is probably completely untrue, since our sources are notoriously unreliable. But here is what is true and what matters for this story. The Pythagorean reaction to the discovery of irrational numbers was not curiosity. It was not excitement. It was suppression. The discovery was treated as dangerous, as something that needed to be hidden. And whether or not anyone was literally drowned, the legend encodes a real historical fact. The first people to discover that reality contains numbers that cannot be expressed as ratios responded not by updating their theory, but by trying to destroy the evidence. I have spent a genuinely embarrassing number of hours reading through the ancient sources on this, digging through Iamblichus and Pappus and the anonymous scholia on Euclid, and the thing that strikes me every time is how modern that reaction feels. Confronted with data that contradicts the model, the instinct is not to fix the model. The instinct is to bury the data. And this instinct did not end with the Pythagoreans. It followed the problem of irrational numbers like a shadow through Cantor in the 19th century and Brouwer in the 20th, and the set theorists of today. But I am getting ahead of myself. This story does not start with a drowning. It starts with a square. And to understand why a square could break a civilization's understanding of reality, you need to understand what the Pythagoreans actually believed and how seriously they believed it. The community Pythagoras founded in Croton, in what is now the southern Italian region of Calabria, around 530 BCE, was not a university. It was not a philosophy department. It was, by any honest description, a cult. Pythagoras himself, born around 570 BCE on the island of Samos off the coast of modern Turkey, emigrated at approximately age 40 to Croton, part of the Greek colonial region known as Magna Graecia, and established his community there. He wrote nothing. Everything we know about him comes from later writers, some writing centuries after his death. The scholar Walter Burkert, in his landmark 1972 study Law and Science in Ancient Pythagoreanism, argues that the early evidence suggests Pythagoras was primarily famous not as a mathematician, but as an expert on the soul's fate after death, a wonder worker, and the founder of a strict way of life. Whether he was truly a mathematician at all remains debated among historians. What is not debated is the nature of his community. New initiates underwent a 5-year period of silence. They listened to teachings from behind a curtain without being permitted to see the teacher's face. They surrendered all personal property upon joining, living under the principle that all things are common among friends. If a member left the community, their property was returned and a tombstone was erected for them. They were considered dead. Iamblichus listed 235 Pythagoreans by name. including 17 women, described as the most famous female members. The community was divided into two classes: the acousmatikoi, the listeners who focused on religious and ritualistic teachings and treated Pythagoras' sayings as divine dogma, and the mathematikoi, the learners who pursued mathematical and scientific inquiry. The relationship between these two groups was contested even in antiquity. The Pythagoreans had strict dietary rules, the most famous being a total prohibition on fava beans. Ancient writers offered wildly different explanations. Aristotle said beans were banned because their shape resembled the cosmos, or because they were used for voting, and the Pythagoreans favored oligarchy. Pliny said they contained the souls of the dead. Diogenes Laertius said the flatulence they caused took away the breath of life. A modern theory links the prohibition to phavism, a genetic enzyme deficiency common in Mediterranean populations, where eating fava beans can trigger severe hemolytic anemia. On vegetarianism, the sources contradict each other flatly. Eudoxus of Cnidus wrote that Pythagoras not only abstained from animal foods, but even kept his distance from cooks and hunters. But Aristoxenus, who grew up in the Pythagorean city of Tarentum and had first-hand knowledge of the community's practices, insisted Pythagoras was not a strict vegetarian and ate certain meats. Both were 4th century BCE sources. You take your pick. Daily life followed a rigid structure: morning solitary walks, then exercise, then breakfast of bread and honey, a period of study and work, afternoon walks in groups of 2 or 3 for philosophical discussion, communal dinner in groups of 10, beginning with libations, ending with reading and discussion of moral philosophy, silence after lights out. Morning and evening, Pythagoreans gathered in circles with a lead singer. They believed music purified the soul, as medicine purified the body. And the reason they believed this connects directly to why the square root of 2 was so devastating. The founding legend of Pythagorean mathematics says Pythagoras was walking past a blacksmith shop and noticed that the hammers produced harmonious sounds when struck. He found the hammers weighed 12, 9, 8, and 6 units. The ratio 12 to 6 is 2 to 1, which produces an octave. 12 to 8 is 3 to 2, the perfect fifth. 12 to 9 is 4 to 3, the perfect fourth. 9 to 8 is the whole tone. These are simple ratios of small whole numbers, and they produce the most consonant musical intervals. The hammer story, first recorded by Nicomachus of Gerasa in the 1st or 2nd century CE, is almost certainly false. The proportions do not work for hammer weights, but they are correct for string lengths on a monochord, the single string instrument credited to Pythagoras, and the earliest credible reference from Xenocrates in the 4th century BCE confirms that Pythagoras discovered the musical intervals do not come into being apart from number. Hippasus himself is credited in a scholium on Plato's Phaedo with experiments using bronze discs of varying thickness to independently demonstrate the fundamental musical ratios. The point is this: the Pythagoreans had real empirical evidence that whole number ratios govern the most fundamental patterns in nature: musical harmony, the geometry of regular solids, the relationships between planetary orbits, which they believed produced a cosmic music, the harmony of the spheres, a sound they said only Pythagoras himself could hear. This concept influenced thinkers for millennia, all the way to Kepler, who published Harmonices Mundi in 1619, explicitly building on the Pythagorean idea that planetary orbits follow musical ratios, the sacred tetracties, a triangular arrangement of 10 dots, 1 plus 2 plus 3 plus 4 equals 10, encoded the fundamental musical consonances and was so revered that Pythagoreans swore oaths by it. For the Pythagoreans, number, arithmos, meant positive integers. All quantities were understood as ratios of these integers. This was not simply a mathematical preference, it was a cosmological commitment. Numbers were the substance of reality. And this is precisely why the discovery of incommensurable quantities was not merely surprising. It was existentially threatening. There is a detail about the Pythagorean community that I have not mentioned yet because I was saving it for this moment. The Pythagoreans did not just believe numbers described reality. They believed numbers were divine. The tetracties, the triangular arrangement of 10 dots, was not a teaching aid. It was a sacred object. Members swore their most binding oaths by it. Iamblichus records the oath. I swear by him who has transmitted to our souls the tetracties, the fountain root of ever-flowing nature. The numbers 1 through 4, which sum to 10, encoded what the Pythagoreans believed were the fundamental structures of existence. 1 was the point. 2 was the line generated by the motion of a point. 3 was the surface generated by the motion of a line. 4 was the solid generated by the motion of a surface. And the ratios between them, 2 to 1, 3 to 2, 4 to 3, produce the octave, the fifth, and the fourth, the three consonances that underpinned all of music. Mathematics was not a tool for the Pythagoreans. It was theology. This is why the square root of 2 was not merely a mathematical inconvenience. It was a heresy, a number that exists, that geometry demands, but that cannot be expressed as a ratio of whole numbers, cannot be captured by the tetracties, cannot be spoken. In a framework where numbers are divine and ratios are the language of divinity, an inexpressible number is not just a problem. It is a blasphemy, a crack in the face of God. I think this is the part of the ancient story that modern tellings usually miss. We present the Pythagorean crisis as an early version of a mathematical problem, a discovery that caused some intellectual discomfort. But that framing misses the stakes entirely. For the Pythagoreans, the discovery of incommensurability was not an intellectual problem. It was a spiritual catastrophe. It meant the cosmos was not, at bottom, orderly. It meant divinity had gaps. It meant their entire understanding of the relationship between mind and reality, between the human soul and the structure of the universe, was fundamentally wrong. And the truly chilling part is that they were right to be scared, not for the theological reasons they imagined, but because the crack they found in the 5th century BCE has, over the course of 25 centuries, spread all the way through the foundations of mathematics and out the other side into the foundations of physics. The thing they were afraid of was real. They just did not know how real. Now let me walk you through the proof that destroyed their world. Take a square, sides of length 1, measure the diagonal. By the Pythagorean theorem, the diagonal d satisfies d squared equals 1 squared plus 1 squared equals 2. So d equals the square root of 2. Now assume, as the Pythagoreans would, that this number can be written as a ratio of two whole numbers, p over q, reduced to lowest terms so they share no common factor. Square both sides. You get 2 equals p squared over q squared, which means p squared equals 2 times q squared. Since p squared is 2 times something, p squared is even. And if p squared is even, p itself must be even, because the square of an odd number is always odd. So write p as 2r. Substitute 4r squared equals 2q squared. Simplify. Q squared equals 2r squared. By the same logic, q squared is even, so q is even. But now both p and q are even, meaning they share a factor of 2. We assumed they had no common factor. Contradiction. The assumption that the square root of 2 is a ratio of whole numbers leads to a logical impossibility. Therefore, no such ratio exists. Aristotle alludes to this proof in his Prior Analytics, noting that the diagonal of a square is incommensurate with its side, because the assumption of commensurability leads to odd numbers equaling even numbers. The proof also appears as an appendix to Book 10 of Euclid's Elements, sometimes cited as Proposition 117, though scholars including Thomas Heath agree it was a later interpolation. The discovery is generally dated to the 5th century BCE. Plato's Theaetetus, written around 369 BCE, describes how Theodoros of Cyrene proved the irrationality of the square roots of 3, 5, and so on up to 17, but started at 3, implying the square root of 2 case was already known from earlier work. I want you to sit with the proof for a moment, because we learn it in school and it feels routine. But imagine you are a Pythagorean. You have built your entire understanding of reality, your religion, your community, your cosmology, on the premise that all quantities are ratios of whole numbers. And now someone has demonstrated, using your own theorem, that the most basic geometric object, a square, contains a quantity that your framework cannot express. The proof does not say we have not found the right ratio. It says the ratio cannot exist. This is not a gap in knowledge. It is a gap in reality, at least in the Pythagorean version of reality. The Greek mathematical tradition pivoted after this. Since numbers could no longer be trusted to describe all magnitudes, geometry became the primary framework for rigorous mathematics. The resolution came from Eudoxus of Cnidus, around 350 BCE. His theory of proportions, preserved as Book 5 of Euclid's Elements, Definition 5, found a way to compare magnitudes without requiring them to be commensurable. 2 ratios are equal if, for all positive integers m and n, the ordering relationship between multiples ma and nb is always the same as between mc and nd. This definition works for both commensurable and incommensurable magnitudes. Scholars have noted its stunning abstraction and the fact that it essentially anticipated Richard Dedekind's construction of the real numbers over 2,000 years later. Now I want to slow down here, because we are about to leave ancient Greece and jump 2,000 years forward. And I do not want you to miss what just happened. The Pythagoreans discovered that reality contains quantities their number system cannot express. Their response was suppression. Then Eudoxus found a workaround, a way to handle incommensurable magnitudes without asking what they actually are. And then Greek mathematics moved on, treating geometry as the primary language of continuous quantity for the next 2,000 years. Euclid's Elements, written around 300 BCE, formalized this approach. Book 5 contains Eudoxus's theory of proportions. Books 7 through 9 handle number theory, meaning integers only. And Book 10, the longest and most complex of all 13 books, attributed largely to Theaetetus of Athens, classifies dozens of types of irrational magnitudes. The shift was complete. Numbers meaning the whole numbers and ratios the Pythagoreans loved were no longer trusted to describe continuous quantities. Geometry took over. But notice what did not happen. Nobody answered the question. Nobody said what irrational numbers actually are. Eudoxus showed how to work with them. Euclid formalized the methods. But the ontological question, what is the square root of 2? What kind of thing is it? Where does it live? Was left untouched. The can was kicked down the road for 22 centuries. And when someone finally picked it up, what they found inside was far worse than what the Pythagoreans feared. Pay attention to this next detail, because it explains everything that follows. When 19th century mathematicians returned to the question of what the real numbers are, they were not motivated by philosophical curiosity. They were motivated by embarrassment. The entire edifice of calculus, invented by Newton and Leibniz in the late 1600s and developed into an enormously productive tool over the following century and a half, was built on the assumption that the real number line was a well-defined, continuous object, but nobody could actually define it. Cauchy, Weierstrass, and others had made calculus rigorous by defining limits, continuity, and convergence in precise epsilon-delta terms. But all of those definitions assumed you knew what a real number was, and nobody did. The real number line was the foundation of analysis, and the foundation had no foundation. And this would be disturbing enough if the story ended here. If the square root of 2 were the anomaly the Pythagoreans feared it was, a single crack in an otherwise solid floor. But what mathematicians discovered 23 centuries later is that the square root of 2 was not the crack. It was the first glimpse through the crack at something underneath, something much larger and much stranger. The Pythagoreans made a second error, far more consequential than the first. They assumed the irrational numbers were the exception. One ugly quantity in an otherwise orderly system, a blemish. It took over 2,000 years, but in 1874, a German mathematician named Georg Cantor proved they had it exactly backwards. The irrational numbers are not the exception. They are almost everything. The rational numbers, the tidy fractions the Pythagoreans worshipped, are the exception. And not just a minority, not just a small fraction, a vanishing invisible measure. Zero sliver of nothing. This is, I personally believe, the most underrated result in the history of mathematics, and the fact that it is not common knowledge should bother you. To see what Cantor proved, you first need to understand what countable means. A set is countable if you can list its elements in a sequence, one after another, so that every element eventually appears. The natural numbers are obviously countable. You just list them in order. 1, 2, 3, 4. What Cantor showed first, and what seems impossible when you first hear it, is that the rational numbers are also countable. The rationals are dense. Between any two of them, there is always another one. Between 0 and 1, there are infinitely many. Between any two of those infinitely many, there are infinitely many more. The rationals seem absolutely inexhaustible. And yet Cantor found a way to list every single one of them. Arrange every positive fraction in a grid. The first row is 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on forever. The second row is 2 over 1, 2 over 2, 2 over 3, 2 over 4. Every row goes on forever, and there are infinitely many rows. Every positive fraction appears somewhere in this infinite grid. Now, instead of trying to go across any single row, which would take forever, traverse the grid diagonally. Start at 1/1, go to 2/1, then 1/2, then 1/3, then 2/2, which equals 1. So skip it. Then 3/1, then 4/1, then 3/2, then 2/3, then 1/4. Continue this zigzag pattern, skipping duplicates and fractions that are not in lowest terms. Every positive fraction will eventually appear in the sequence. You can assign each one a natural number. First, second, third. The rationals are countable. They are, in a precise mathematical sense, the same size infinity as the natural numbers. Cantor called this size Aleph null. And then he proved that the real numbers are not. His 1891 proof, the famous diagonal argument, published in the Jahresbericht der Deutschen Mathematikervereinigung, is one of the most elegant constructions in the history of thought. It was first presented at the founding meeting of the German Mathematical Society in Halle, Cantor's home university. Suppose someone hands you a list that claims to contain all real numbers between 0 and 1, written out in their decimal expansions. The first number has some digit in its first decimal place. The second number has some digit in its second decimal place. The third number has some digit in its third decimal place. Now construct a new number by going down the diagonal of this list. Take the first digit of the first number, the second digit of the second number, the third digit of the third number, and so on. Then change every single digit. If it is a 5, make it a 6. If it is anything else, make it a 5. This new number differs from the first number in the first decimal place, from the second number in the second decimal place, from the nth number in the nth decimal place. It cannot be anywhere on the list. Your supposedly complete list was missing at least one real number. And this works for any list whatsoever. No matter how cleverly you construct your enumeration, the diagonal argument generates a number that escapes it. I want to flag something about this proof that does not get enough attention. The diagonal argument is not just a proof that the reals are uncountable. It is a demonstration that the real numbers actively resist cataloging. Any list you construct, no matter how exhaustive, the reals generate an escapee. It is as if the number line has a built-in defense mechanism. You try to pin it down and it slips away. You try to contain it and it produces something you missed. This is not a limitation of human cleverness. It is a structural feature of the continuum itself. The real numbers are in some deep sense uncatchable. I want to walk through the diagonal argument more slowly, because I think the usual presentation goes too fast and misses what makes it genuinely unsettling. Imagine you have infinite patience and infinite paper. You sit down and you try to write a complete list of all real numbers between 0 and 1. You write them in their full decimal expansions, 1 per line. Your list looks something like this. Line 1 might be 0.5000, and so on. Line 2 might be 0.33333 repeating. Line 3 might be 0.141, 5, 9, 2, and continuing. You fill in line after line, each one a real number with its infinite decimal expansion. You can put them in any order you like. You can use any system you can think of. Your list is infinitely long. Now Cantor says, I do not care how you arranged your list. I do not care how clever your system was. I can construct a real number that is not on it. Here is how. Look at the first digit after the decimal point of your first number. Whatever it is, choose a different digit. That is the first digit of my new number. Look at the second digit after the decimal point of your second number. Choose a different digit. That is my second digit. The third digit of my third number. Choose differently. The 100th digit of my 100th number. Choose differently. The millionth digit of my millionth number. Choose differently. I continue this process forever, one digit for each line of your list. The number I have constructed differs from your first number in the first decimal place. It differs from your second number in the second decimal place. It differs from your nth number in the nth decimal place. It is therefore not equal to any number on your list. Your complete list is incomplete, and this is not a trick. There is no loophole. No matter what ordering you choose, the diagonal argument generates a real number you missed. This works for every possible enumeration. The reals are a strictly larger infinity than the natural numbers. They cannot be listed. They are uncountable. Now here is the part that does not get enough attention. Cantor's argument is not just a proof, it is a procedure. It takes any proposed listing of the reals and algorithmically constructs an escapee. The reals do not merely passively resist enumeration. They actively generate counterexamples to any attempt. You give me a list, and the diagonal process hands back a number you forgot. The number line is not just large, it is in some deep structural sense evasive. It fights back against being catalogued. If you want to apply language that sounds almost biological, the continuum has an immune system. It detects any attempt at complete enumeration and produces an antibody. That language is metaphorical, obviously. Numbers do not have intentions, but the structural behavior is real, and it is unlike anything in the countable world. The natural numbers are tame. You can list them. The rationals are tame. You can list them with Cantor's zigzag. The reals are wild. They cannot be contained by any countable process. And this wildness is not peripheral to the real number line. It is the real number line. The countable numbers, the rationals, the ones we can write down and work with, are a measure zero subset. The overwhelming majority of the line is this wild, uncountable, unlistable territory. And Cantor wanted to know, how wild is it? Cantor also proved in his original 1874 paper in Krell's journal that the reals are uncountable using a different method, the nested intervals argument. Given any sequence of real numbers, he showed you can construct a sequence of shrinking closed intervals that avoids every number in the sequence, with a non-empty intersection containing a real not on the list. The diagonal argument came 17 years later as a simpler, more general proof. But here is where it gets worse. The truly disturbing result is what happens when you combine the countability of the rationals with the uncountability of the reals. The rationals are countable. This means they can be listed, and any countable set spread across the real number line takes up no space at all. Here is the proof. List all the rational numbers as Q21, Q2, Q3, and so on. Pick any tiny number epsilon, as small as you want. 1 billionth, 1 trillionth, 1 divided by Graham's number. Now cover Q1 with an open interval of length epsilon over 2. Cover Q2 with an interval of length epsilon over 4. Cover Q3 with an interval of length epsilon over 8. Each rational number gets its own little interval, and each interval is half the size of the previous one. The total length of all these intervals is epsilon over 2 plus epsilon over 4 plus epsilon over 8 plus epsilon over 16, a geometric series that sums to exactly epsilon. You have covered every single rational number with intervals whose total length is epsilon. And epsilon can be made as small as you want. The Lebesgue measure of the rational numbers is 0. If you could throw a dart at the number line with perfect mathematical randomness, the probability of hitting a rational number is exactly 0. Not approximately 0, not vanishingly small. Exactly 0. The rationals are infinitely dense. There is one between any two reals, and yet they occupy no space. They are like an infinitely fine dust spread across the line, present everywhere, and yet amounting to nothing. Henri Lebesgue formalized this in his 1902 doctoral thesis at the Sorbonne, titled Integral Length Area. His measure theory became foundational to all of modern analysis, probability theory, and physics. And the conclusion is inescapable. The irrational numbers are not the cracks in the floor. They are the floor. The rationals are the cracks. And no, I am not making that up. I realize this sounds like the kind of claim that should require more evidence, so let me state it as precisely as possible. The set of rational numbers has Lebesgue measure 0. On the real line, the set of irrational numbers has full measure. If you selected a real number uniformly at random from any interval, the probability of getting a rational number is 0. And the probability of getting an irrational number is 1. This is proved. This is not speculation. This is what the math says. Now here is where I need to tell you about Georg Cantor's life, because his biography is the first chapter in a pattern that repeats throughout this story. The pattern is this: everyone who pressed deeper into the nature of the number line paid a personal price. Cantor was born March 3, 1845, in the western merchant colony of St. Petersburg, Russia, the oldest of 6 children. His father, Georg Waldemar Cantor, was a successful stockbroker whose parents were members of the Sephardic Jewish community of Copenhagen, a fact Cantor confirmed in an 1896 letter to the historian Paul Tannery. His mother, Maria Anna Bohm, was Austro-Hungarian Roman Catholic by baptism, who converted to Protestantism upon marriage. The family was deeply musical. His maternal grandfather, Franz Bohm, had been a soloist in a Russian imperial orchestra, and the young Georg was regarded as an outstanding violinist. The family moved to Germany in 1856 due to the father's failing health. Cantor studied at the University of Berlin from 1863 under 3 of the most prominent mathematicians of the age: Karl Weierstrass, Ernst Kummer, and Leopold Kronecker. He completed his doctorate in 1867 on number theory and took a position at the University of Halle in 1869. He would remain there his entire career, never achieving the prestigious Berlin chair he wanted. In 1874, he married Vali Gutmann. They had 6 children. An inheritance from his father provided crucial financial support, as Halle professors were poorly paid. The common story, the one that has been repeated in popular accounts for a century, is that Cantor went mad studying infinity. that staring into the abyss of transfinite numbers broke his mind. This needs to be corrected, because the truth is more disturbing than the myth. Modern diagnosis points to bipolar disorder, a condition with biological roots that was not caused by mathematical contemplation. What happened to Cantor was not that infinity drove him insane. What happened was that the mathematical establishment, led by one man, waged a campaign of professional destruction against him at precisely the moments when his illness made him most vulnerable. The man was Leopold Kronecker, and the documented record is damning. Kronecker's famous quote, "God made the integers, all else is the work of man," was spoken at the 1886 Berlin Conference of Natural Scientists. The speech itself was not preserved in writing. We know it only from Heinrich Weber's obituary of Kronecker, published in 1893. Linguist Walter Felscher noted that the phrase "lieber Gott," which Kronecker used, is a colloquial expression typically used when talking to children, suggesting the statement may have been partly tongue-in-cheek. But Kronecker's actions were not tongue-in-cheek at all. In 1874, when Cantor submitted his first groundbreaking paper to Crell's journal, Kronecker was the referee. He intentionally delayed publication. The paper appeared only because Richard Dedekind intervened. In 1877, Kronecker tried again to block publication of Cantor's proof that the unit interval and the unit cube have the same cardinality, a result so surprising that Cantor wrote to Dedekind on June 29, 1877, "I see it, but I do not believe it." Cantor was so demoralized by Kronecker's opposition that he wanted to withdraw the paper. Dedekind and Weierstrass talked him out of it, but after this incident, Cantor never again submitted to Crell's journal. He published subsequently in Mathematische Handlungen, supported by Felix Klein, and in Acta Mathematica, edited by Mittag Leffler. Kronecker called Cantor a scientific charlatan, a renegade, and a corrupter of youth. When Ferdinand Lindemann proved the transcendence of pi in 1882, Kronecker reportedly asked, "Of what use is your beautiful investigation regarding pi, since irrational numbers do not exist?" I should note, in fairness, that the historian Harold Edwards has argued Kronecker was more nuanced than the villain of mathematical legend. Kronecker apparently insisted that a disagreement over mathematical questions should not affect personal relations. And in 1891, Cantor invited Kronecker to give the opening address at the first German Mathematical Society meeting. Kronecker had to decline because his wife had been fatally injured in a climbing accident. He died December 29th of that year. The relationship was complicated, but the professional damage was real and documented through the Cantor-Dedekind correspondence, published by Emmy Noether and Jean Cavais in 1937. Cantor's first hospitalization came in May 1884, a severe depression. He recovered and turned to studying Elizabethan literature and the question of whether Francis Bacon wrote Shakespeare's plays. A second crisis came in 1890. On December 16th of that year, his youngest son Rudolf died suddenly while Cantor was out delivering a lecture on the Baconian theory. Further hospitalizations followed in 1903. Then, in 1904, an especially agitating incident occurred at the International Congress of Mathematicians in Heidelberg, where Julius Koenig presented a paper claiming to disprove transfinite set theory. The paper was read in front of Cantor's daughters. It was later found to contain a fundamental error, but the damage was done. After that, hospitalizations recurred at intervals of roughly 2 to 3 years. In June 1917, Cantor entered a sanatorium for the last time. His letters to his wife from this period consist mostly of requests to come home. He died on January 6, 1918, of a heart attack, malnourished during wartime rationing, in the Halle University Psychiatric Clinic. The public celebration of his 70th birthday, planned for 1915, had been cancelled because of World War I. I want to zoom in on the Cantor-Kronecker conflict for a moment longer, because I think it illuminates something important about how institutions handle inconvenient truths, and because it connects to the broader pattern of suppression that runs through this entire story. Cantor's letter to Dedekind, after proving that the unit interval and the unit cube have the same cardinality, is one of the most famous letters in the history of mathematics. I see it, but I do not believe it. He wrote those words in French, "Je le vois, mais je ne le crois pas," on June 29, 1877. The result was genuinely shocking. A one-dimensional line and a two-dimensional square and a three-dimensional cube all contain exactly the same number of points. Dimension, one of the most basic properties of geometric space, makes no difference to the size of the continuum. This is the kind of result that even today makes your brain itch when you try to accept it, and Cantor's contemporaries did not accept it easily. Kronecker's opposition is the most documented, but he was not alone. Mittag Leffler, the editor of Acta Mathematica, who had been one of Cantor's supporters, asked Cantor in 1885 to withdraw a paper he had submitted because it was, in Mittag Leffler's words, about 100 years too early. Cantor was devastated. He wrote to Mittag Leffler in response, and then ceased publishing mathematical papers for 6 years. Poincaré, the great French mathematician, dismissed Cantor's transfinite numbers as a disease from which mathematics would eventually recover, though scholars have debated the exact attribution of this quote. Jeremy Gray investigated it in a 1991 article in the Mathematical Intelligencer and found the evidence thin, but the essential dynamic was consistent. Cantor discovered something true about the real number line, something provable, something that has been verified and re-verified, and now forms bedrock mathematics. And the establishment's response was not to engage with the mathematics, it was to attack the mathematician, to delay his publications, to block his career advancement, to call him a charlatan. Cantor wrote in 1883, in the preface to his Grundlagen, a remarkable line: "The essence of mathematics lies in its freedom." He was, in context, defending the right of mathematicians to introduce new concepts, even when those concepts provoke discomfort. He was defending his own right to study infinity against people who wanted him to stop. That line is now famous, but the man who wrote it died in a sanatorium. And Cantor's central question, his continuum hypothesis, was the thing he could never resolve. He proposed it in 1878. He worked on it for decades. He wrote to Dedekind about it obsessively. He presented it at conferences. He was convinced at various points that he had proved it, then disproved it, then proved it again. The question consumed the best years of his intellectual life, and he never answered it. Hilbert's defense was magnificent, but also, in hindsight, poignant. He declared Cantor's paradise sacrosanct and then listed the continuum hypothesis as the most important unsolved problem in mathematics. He was staking the prestige of the entire field on the assumption that the problem could be solved. That with enough effort, enough ingenuity, the answer would come. But Hilbert was operating under the assumptions of his own program, the belief that every well-posed mathematical question has a definite answer. Gödel would destroy that belief within 5 years of Hilbert's retirement address. Cantor had proved two infinities exist: Aleph null, the countable infinity of the natural numbers and rationals, and the continuum, the uncountable infinity of the reals. But he believed something specific about their relationship. He believed there was nothing in between. No infinity bigger than Aleph null, but smaller than the continuum. He called this the continuum hypothesis, and he spent the rest of his working life trying to prove it. He failed. He alternated between claiming he had proved it true, then false, then giving up entirely. In 1900, David Hilbert put the continuum hypothesis first on his list of 23 problems for the new century, presented at the International Congress of Mathematicians in Paris. The greatest mathematicians in the world attacked it for the next 60 years. And what they found was not an answer. It was something that should disturb you far more than any answer could. But first I need to tell you about Richard Dedekind, because his construction of the real numbers in 1872 is the foundation on which all of this rests, and it reveals something strange about the object we are talking about. Dedekind was born October 6, 1831, in Braunschweig, Germany. He was the last doctoral student of Carl Friedrich Gauss at Göttingen. On October 24, 1858, while teaching calculus for the first time at the Zurich Polytechnic, he had the insight that would define his career. He was using the real number line in his lectures every day, but could not actually define what it was. The rationals were well defined, ratios of integers. But the irrationals, the numbers that Hippasus had died for, what were they exactly? A Dedekind cut is a partition of the rational numbers into two non-empty groups, such that every number in the first group is less than every number in the second. Every rational number produces such a cut, but there are cuts that no rational number produces. The cut where the first group contains all rationals whose square is less than 2, and the second contains all rationals whose square is greater than 2. No rational number sits at the boundary. The boundary is the square root of 2, which is not rational. Dedekind's move was audacious. Whenever a cut is produced by no rational number, we create a new number into existence. The irrational numbers are the gaps in the rationals. The real number line is the rationals plus all their gaps. He published this in 1872, 14 years after the insight, under the title Continuity and Irrational Numbers. That same year, he met Cantor while on holiday in Interlaken, Switzerland, beginning their fateful collaboration. I want to pause on Dedekind for a moment, because his story is quieter than Cantor's or Gödel's, but in some ways more revealing. Dedekind was by all accounts a modest and careful man. He was born in Braunschweig, Germany on October 6, 1831, and he died in the same city on February 12, 1916, at the age of 84. He was Gauss's last doctoral student at Göttingen, which is a little like being the last apprentice of Leonardo da Vinci. He never married. He lived with his sister Julie for most of his adult life. He taught at the Brunswick Polytechnic, a relatively obscure institution, and declined multiple offers from more prestigious universities because he did not want to leave his hometown. He had his key insight about the real numbers on a specific date, October 24th, 1858. While preparing his first calculus course, he sat down to explain to students What happens when you cut the number line at an irrational point? And he realized he could not actually define what the number line was. That bothered him. It bothered him so much that he spent the next 14 years working out a rigorous answer before publishing it. 14 years, from the insight to the publication. In an era when mathematicians regularly published half-baked ideas and fought over priority, Dedekind sat on one of the most important constructions in the history of mathematics for 14 years because he wanted to get it right. And here is the thing about Dedekind's construction that I think carries enormous weight for our story. When he finally published Continuity and Irrational Numbers in 1872, he included a passage that amounts to a confession. He acknowledged that his definition creates numbers by fiat. Whenever a cut in the rationals is not produced by any rational number, he wrote, we create a new, an irrational number, which we regard as completely defined by this cut. We create, not we discover, not we find. We create. Dedekind was not a Platonist. He did not claim irrational numbers were sitting out there waiting to be found. He said we bring them into existence by an act of mathematical will. This is a subtle but crucial distinction, and it connects directly to the crisis that would erupt decades later between the Platonists and the constructivists. If irrational numbers are created by definition rather than discovered in nature, then what is the real number line? Is it an objective feature of reality? Or is it a human construction? And if it is a construction, do we have the right to construct non-computable numbers, numbers that no process can generate and no language can describe? Dedekind's quiet, careful word choice, we create, planted a seed that would grow into one of the deepest philosophical disputes in the history of thought. But here is the thing about Dedekind's construction that gets overlooked. He defined the irrational numbers as absences, gaps, holes in the rational line, and we have already established that these gaps constitute almost all of the number line. The rationals have measure 0. The irrationals have full measure. So the real number line, the continuum, is overwhelmingly composed of absences, of things defined by what they are not. The substance of the number line is made of ghosts. And when Cantor tried to determine the most basic structural property of this ghostly object, whether there is an infinity between the countable and the continuum, the object refused to answer. David Hilbert, the most influential mathematician of the early 20th century, defended Cantor against Kronecker and the skeptics. No one shall expel us from the paradise that Cantor has created. He declared on June 4, 1925, in a lecture at Münster published the following year in Mathematische Annalen, volume 95, page 170. He also described Cantor's work as the finest product of mathematical genius and one of the supreme achievements of purely intellectual human activity. Hilbert believed all mathematical problems could be solved. He believed in the completeness of formal systems. He staked his career on it. And he was wrong. Because over the next 45 years, the two greatest logicians of the 20th century would prove that the continuum hypothesis is not merely unsolved, it is unsolvable. Within our axioms, permanently. Kurt Gödel was born April 28, 1906, in Brunn, Austria-Hungary, now Brno in the Czech Republic. His childhood nickname was Der Herr Warum, Mr. Why? Because he peppered every adult with incessant questions. He studied at the University of Vienna, became associated with the Vienna Circle, and completed his doctorate in 1929, proving the completeness of first-order predicate logic. In 1931, at age 25, he published a paper in Monatschäfte für Mathematik und Physik that destroyed the most ambitious project in the history of mathematics. His first incompleteness theorem proved that any consistent formal system capable of expressing basic arithmetic contains true statements the system cannot prove. His second proved such a system cannot prove its own consistency. Hilbert's program, the effort to formalize all of mathematics and prove it sound, was logically impossible. Not impractical, impossible. Here is something about Gödel's life after the incompleteness theorems that I think is essential to this story and rarely told properly. After proving the consistency of the continuum hypothesis in 1940, Gödel became increasingly reclusive and fixated on philosophy. He was a close friend of Albert Einstein at the Institute for Advanced Study in Princeton, and the two walked together daily. Einstein reportedly said he went to the Institute only for the privilege of walking home with Gödel. But Einstein died in 1955, and Gödel lost his closest companion. Gödel's philosophical views were extreme. He was a committed Platonist who believed mathematical objects exist as objectively as physical objects. He believed the human mind is not a machine, that Turing machines cannot capture human mathematical intuition, and that there are mathematical truths that no formal system can prove, but that humans can nevertheless perceive. He also developed a formal proof of the existence of God, based on modal logic, which he showed to only a few people during his lifetime, fearing ridicule. It was published posthumously. His paranoia about poisoning developed gradually and intensified after Einstein's death. By the 1970s, it had become severe. His wife Adele, who was not an intellectual but was fiercely protective, was his lifeline. She prepared all his food. When she had a stroke in late 1977 and was hospitalized for an extended period, Gödel simply stopped eating. He was admitted to Princeton Hospital on December 29, 1977, weighing only about 65 pounds. He died 2 weeks later, on January 14, 1978. The official cause on the death certificate reads, malnutrition and inanition caused by personality disturbance. Think about that. The man who proved that formal systems contain truths they cannot verify died because he could not verify the safety of his own meals. The man who showed mathematics its own limits was destroyed by his own limits. There is a terrible symmetry in that, and I do not want to overinterpret it, but I also do not want to let it pass without comment. The continuum problem, the incompleteness theorems, the nature of mathematical truth. These are not questions that leave the people who work on them unaffected. They reach into the foundations of certainty itself. And for some of the people who went deepest, the foundations gave way. The timing is almost too perfect. On September 8th, 1930, in Königsberg, Hilbert delivered his retirement address. The final line, later recorded for radio and inscribed on his tombstone, "We must know, we will know." The day before, at the same conference, 24-year-old Gödel had quietly announced in a discussion session that he had proved the opposite. Hilbert was apparently not in the room. I have been obsessed with that piece of timing since I first read about it. There is something unbearable about it. The most famous mathematician alive declaring victory at the podium while a young logician sits in the audience, holding the proof of defeat. Gödel then turned to the continuum hypothesis. In the summer of 1930, He began thinking about it. By 1937, he had his result. He constructed the constructible universe, designated L, built through transfinite recursion. At each level, you take everything built so far and add only sets that can be explicitly defined. L is the most parsimonious model of set theory that still satisfies all the ZFC axioms, and in L, both the axiom of choice and the continuum hypothesis hold true. Gödel announced this in December 1938 in the Proceedings of the National Academy of Sciences. The full monograph appeared in 1940 as a slim 66-page volume published by Princeton University Press. The result was this: if ZFC is consistent, then ZFC plus the continuum hypothesis is also consistent. You cannot use the standard axioms to disprove CH. That was half the puzzle. But Gödel believed the continuum hypothesis was actually false. He wrote in a landmark 1947 paper in the American Mathematical Monthly that it is very suspicious that no plausible proposition implying CH had been found. While numerous plausible propositions implied its negation, he believed new axioms would eventually settle the question. Gödel was a mathematical Platonist his entire adult life. He believed mathematical objects exist independently of human thought. He told Hao Wang that in principle, we can know all of mathematics. It is given to us in its entirety and does not change. He had been a realist since about 1925. In his 1951 Gibbs lecture, he said concepts form an objective reality of their own, which we cannot create or change, but only perceive and describe. He died January 14th, 1978, in Princeton. Cause of death on the certificate was starvation and inanition due to personality disorder. He had become convinced his food was being poisoned. He would eat only food prepared by his wife Adele. When Adele was hospitalized for an extended period, Gödel simply stopped eating. The greatest logician of the 20th century died because the person he trusted to verify the safety of his food was no longer available. I think about that a lot. There is something about Gödel's paranoia that mirrors his mathematical work. His theorems proved that formal systems cannot fully verify their own soundness. His life ended because he could not verify the soundness of his own meals. But the continuum hypothesis needed more than Gödel's half. It needed someone to prove the other direction, and that someone could not have been more different. Paul Joseph Cohen was born April 2nd, 1934, in Long Branch, New Jersey, the youngest of 4 children. His parents Abraham and Minnie were Jewish immigrants from Poland. Abraham was described as basically an odd-job man, and Minnie did dressmaking. The parents separated when Paul was 9. He was raised by his mother in Brooklyn. At age 9, his sister Sylvia went to the New York Public Library and checked out a calculus textbook for him. Not a pop science book, a calculus textbook. He graduated from Stuyvesant High School in 1950 at age 16. Cohen enrolled at Brooklyn College but left without a bachelor's degree after 2 years, having learned he could begin graduate work at the University of Chicago. He earned a master's in 1954, initially studying under Andre Weil. His PhD came in 1958 under Antony Zygmund with a dissertation on trigonometric series. He was an analyst, not a set theorist, not a logician. This is the detail about Cohen's story that I think is most remarkable, and it is the one most often glossed over. The man who solved one of the most important problems in the foundations of mathematics was not a specialist in foundations. He was an outsider. His friend Eli Stein described his personality. What drives Cohen is that he is going to be better than any other guy. He is going to solve the big problems. Sylvia Nazar wrote that he spoke several languages, played the piano, and his ambitions were seemingly unlimited. Cohen began working on the independence of the continuum hypothesis toward the end of 1962. He later recalled that he had the feeling that people thought the problem was hopeless, since there was no new way of constructing models of set theory. By mid-April 1963, the essential ideas had crystallized. He described the experience. There are certain moments in any mathematical discovery when the resolution of a problem takes place at such a subconscious level that, in retrospect, it seems impossible to dissect it and explain its origin. Rather, the entire idea presents itself at once, often perhaps in a vague form, but gradually becomes more precise. He was 29. Cohen's technique, forcing, was genuinely new. The idea is to start with a model of set theory and carefully add new elements, generic reals, that are maximally bland, having no special properties relative to the original model. The statements true in the expanded model are only those forced to be true by the forcing conditions. The critical technical challenge was adding enough new reals to make the continuum larger than Aleph-1 while preserving cardinals, ensuring Aleph-1 in the old model stays Aleph-1 in the new one. Cohen solved this using a topological lemma due to N.A. Shanin, which he recalled while on vacation with his family in the Midwest. I love this detail. One of the most important breakthroughs in 20th century mathematics happened because a guy on a family road trip remembered a topology lemma. On April 24th, 1963, Cohen sent his first letter to Gödel. A second, more urgent letter followed, expressing fear of a flaw and frustration with logicians who could not believe he had proved the key theorem. On May 9th, he sent the actual proof. Gödel wrote back, "Let me repeat that it is really a delight to read your proof of the independence of the continuum hypothesis. I think that in all essential respects, you have given the best possible proof, and this does not happen frequently. Reading your proof had a similarly pleasant effect on me as seeing a really good play." Cohen presented the result at Berkeley on July 4th, 1963. The paper appeared in the Proceedings of the National Academy of Sciences in December. In his revised 1964 postscript, Gödel called it the greatest advance in the foundations of set theory since its axiomatization. Andrzej Mostowski called it the most important advance since Gödel's own 1940 monograph. There is a reason this story is still talked about today, and it is not because of the mathematics. It is because of the human cost. I keep a mental list of what happened to the people who pushed deepest into the continuum problem. Hippasus, drowned or exiled or erased. Cantor, dead and malnourished in a psychiatric clinic. Gödel, starved to death. Brouwer, expelled from the mathematical establishment, spent decades in isolation, killed by a car in front of his own house. Cohen is the exception. He lived a full life, had a family, won every prize the field had to offer. But even Cohen, who was by all accounts a robust and confident personality, described the moment of his discovery in terms that sound almost mystical. A resolution occurring at such a subconscious level that it seems impossible to dissect its origin. The problem touches something deep. The people who work on it do not come away unchanged. I do not want to romanticize this. Mental illness is not caused by studying mathematics. Cantor's bipolar disorder and Gödel's paranoia had biological roots that would have existed regardless of their research topics. But the specific form of their struggles, the specific manifestation, is hard to separate from the nature of the questions they were asking. Cantor was trying to determine the size of the infinite, and the infinite refused to cooperate. Gödel proved that formal systems cannot verify their own soundness, and spent his final years unable to verify the safety of his own food. There is a poetic cruelty in these parallels that I think is worth acknowledging, even as we resist the temptation to draw causal arrows where none exist. What I can say with confidence is that the continuum problem has a strange gravitational pull. It draws people in and does not let them go. Cantor worked on it for decades. Gödel returned to it repeatedly throughout his career, despite making his reputation on other results. Cohen, who was not even a set theorist, felt compelled to attack it. And today, 70 years after Cohen's proof, the question is still generating new research programs, new axiom candidates, and new philosophical positions. It is the open wound of mathematics. It does not heal. Cohen received the Fields Medal in 1966 at the International Congress of Mathematicians in Moscow. It remains the only Fields Medal ever awarded for mathematical logic. He married Christina Karls on October 10, 1963. He spent his career at Stanford, gave a lecture on his continuum hypothesis proof at the Gödel Centennial in Vienna in 2006, and died March 23, 2007, at 72. The combined result is this: the continuum hypothesis is independent of ZFC. It can be true or false, depending on which set theory you adopt. Both are consistent. The analogy is the parallel postulate. For 2,000 years, mathematicians tried to derive Euclid's fifth postulate from the others. Bolyai, Lobachevsky, and Riemann proved you can have geometries where it holds, and geometries where it fails. Same with the continuum hypothesis. Now, you may have heard the continuum hypothesis described as an unsolved problem. I need to correct that, because the distinction is crucial. It is not unsolved the way the Riemann hypothesis is unsolved, where we simply have not found the proof yet. Gödel and Cohen proved the proof does not exist within our axioms. Not that we have not found it, that it cannot exist. That is a categorically different kind of unknowing. There is one more thing about Cohen's proof that I want to highlight, because it gets at something the popular accounts always miss. Forcing did not just solve one problem. It created a method. After Cohen, set theorists had a tool for building models of set theory with essentially any desired properties. You want a universe where the continuum is Aleph 2. Forcing can build it. Aleph 17? Forcing can build it. Aleph Omega? Yes. In fact, the only constraint is a theorem proved by Easton in 1970 that says the continuum can be any cardinal with uncountable cofinality. The freedom is almost total. This means the continuum hypothesis is not just independent. It is wildly underdetermined. There is not a handful of competing candidates for the size of the continuum. There are, in principle, infinitely many. Any one of a vast range of infinite cardinalities is consistent with our axioms. The number line does not have one possible size that we cannot determine. It has infinitely many possible sizes, and our axioms cannot distinguish between them. I think about this fact more than is probably healthy. We are accustomed to thinking of the number line as a fixed, definite object, a thing with a specific structure that exists whether we understand it or not. But if Cohen's result is taken at face value, the number line does not have a fixed size, or rather, our formal systems cannot pin down what that size is, and the range of possibilities is not narrow. It is as wide as the transfinite numbers themselves. When Cantor first proved the reals are uncountable, the natural assumption was that the continuum was Aleph 1, the very next infinity after Aleph null. That was the continuum hypothesis. It seemed obvious. It seemed inevitable. The fact that it can be literally anything, that the gap between the countable and the continuum can be as small as one step or as large as you like, is the kind of result that should make you question whether the word size even means what you think it means when applied to infinite sets. Let me tell you what the independence result actually means in practice, because I think the analogy to the parallel postulate, while correct, does not convey the full weight of what is going on. In geometry, the independence of the parallel postulate meant there are different geometries. Euclidean geometry, where parallel lines never meet. Hyperbolic geometry, where they can diverge. Elliptic geometry, where they always converge. Each one is internally consistent. Each one has applications. We use Euclidean geometry for building houses and hyperbolic geometry for modeling certain physical systems, and elliptic geometry for navigating the surface of the Earth. The independence of the parallel postulate was liberating. It expanded the toolkit. It did not feel like a crisis. It felt like a discovery. The independence of the continuum hypothesis does not feel that way. And the reason is this. Nobody cares how many parallel lines you can draw through a point, not on a given line. It is an axiom about geometry, and different geometries are useful for different things. But the continuum hypothesis is about the structure of the number line, not a number line, the number line, the one underlying all of analysis, all of physics, all of computation. If the continuum hypothesis is independent, that means there are set theories where the number line has one structure and set theories where it has a fundamentally different structure, and our axioms cannot tell which one is real. This is not expanding the toolkit. This is discovering that the foundation of the house has no fixed shape, and the architect cannot determine what shape it should be. Gödel saw this clearly. He wrote in 1947 that he expected new axioms to be discovered that would settle the question. He believed the continuum hypothesis was false and that the right axioms would show this. He spent decades looking for those axioms. He never found them. And the reason he never found them, as it turns out, is that the two most natural candidates for new axioms, large cardinal axioms which assert the existence of very large infinite sets, provably cannot settle the continuum hypothesis. This was shown by Azriel Levy and Robert Solovay in the 1960s. Large cardinals resolve almost every other question in set theory. They form a beautifully ordered hierarchy, each level more powerful than the last. But they are completely blind to the continuum hypothesis. The one question Gödel most wanted them to answer is the one question they cannot touch. That is not a technical footnote. That is a fundamental feature of mathematical reality. The most natural extensions of our axioms, the ones that settle everything else, cannot settle this. It is as if the continuum hypothesis lives in a blind spot of mathematical knowledge, a region that our most powerful tools cannot illuminate. Cohen himself took a more radical view. He was a formalist, meaning he did not believe mathematical statements have truth values independent of the axioms. For Cohen, proving the independence of CH was essentially the same as settling it. The question has no answer, because there is no fact of the matter. There is no Platonic real number line sitting out there with a definite structure that we are failing to detect. There are just axiom systems, and different axiom systems give different answers. And that is all there is to say. When Cohen was asked whether he thought CH was true or false, he said he tended toward thinking it was false. But more importantly, he did not think the question was meaningful in the way most people assumed. This brings us to the current state of affairs, which is, frankly, a mess. And I mean that in the most respectful way possible. The people working on this are among the smartest mathematicians alive, but they cannot agree on what they are even trying to do. Wooden's story is the most dramatic. He is widely regarded as the leading set theorist of his generation. Born April 23, 1955, in Tucson, Arizona. PhD from Berkeley in 1984 under Robert Solovay. Now at Harvard. In 2001, he published 2 landmark papers in the Notices of the American Mathematical Society, arguing that the continuum hypothesis is false and that the continuum has cardinality Aleph-2. He developed a sophisticated framework called omega logic and proposed the star axiom as a new foundation. The star axiom implied that there is exactly one infinity between the countable and the continuum, falsifying CH in a very specific and natural way. Then, starting around 2010, Wooden changed his mind. He began developing the Ultimate L program, which proposes an inner model of set theory that would validate CH rather than refute it. As Colin Rydberg documented in Archive for History of Exact Sciences in 2015, Wooden's arguments from 1990 through 2004 said CH was incorrect, while from 2010 onward he presented a very different argument that CH might be true. The man at the top of the field argued both sides within a single career. If that does not tell you the problem is hard, nothing will. Meanwhile, the forcing axioms, Martin's maximum and the proper forcing axiom, which are among the most natural and well-studied alternatives to CH, all point towards CH being false, with the continuum equal to Aleph-2. An independent proof in 2021 showed that Wooden's own star axiom follows from a variation of Martin's maximum, tightening the case for Aleph-2. But Ultimate L, if completed, would give CH. The 2 programs point in opposite directions, and both are being pursued by serious mathematicians at serious institutions. Saharon Shila, perhaps the most prolific living set theorist, has taken a pragmatic stance. He wrote that he does not agree with the pure Platonic view that the interesting problems in set theory can be decided. My mental picture is that we have many possible set theories all conforming to ZFC. Joel David Hampkins goes further with his multiverse view, arguing that the continuum hypothesis is settled, not by finding the right answer, but by understanding how it behaves across the full landscape of set theoretic universes. Solomon Pfefferman argued that CH is not a definite mathematical problem at all, that it simply has no truth value, like asking whether the number 7 is green. This is the state of human knowledge about the most basic structural property of the real number line, the object that underpins all of analysis, physics, engineering, and computation. The experts cannot agree on whether the question has an answer, let alone what the answer is. And here is where it gets worse, because the independence result is a symptom of something deeper about the real number line itself. something that makes the Gödel-Cohen result look almost comforting by comparison. In 1975, Gregory Chaitin, who had independently discovered algorithmic information theory as a teenager at the Bronx High School of Science, parallel to Kolmogorov's work and Solomonov's, defined a number called omega. Omega is the halting probability of a universal prefix-free Turing machine, the probability that a randomly chosen program will halt rather than running forever. It is a perfectly well-defined real number between 0 and 1, and it is uncomputable. No algorithm can calculate its binary expansion. Each bit encodes the answer to a halting problem, and Turing proved in 1936 that the halting problem is undecidable. Chaitin put it this way: whether each bit of omega is a 0 or a 1 is a mathematical fact that is true for no reason. It is true by accident. But omega is not the point. Omega is an example. The point is what it reveals about the number line as a whole. The set of all possible computer programs is countable. Programs are finite strings of symbols. You can list them. Therefore, the set of computable real numbers, numbers whose digits can be generated by some algorithm, is also countable. And countable sets have Lebesgue measure 0. Almost all real numbers are uncomputable. Let that sit for a moment. Almost all real numbers cannot be calculated by any algorithm approximated by any finite process. They exist in whatever sense mathematical objects exist, but no computer running for any length of time could ever produce them. And it is worse still, the set of all possible descriptions in any language, English, Mandarin, first-order logic, any symbolic system, is also countable. Descriptions are finite strings. There are only countably many finite strings, which means there exist real numbers that cannot even be described, not computed, not named, not defined, not referred to by any finite expression in any language ever spoken or ever possible. They are unknowable. They exist and yet cannot be the object of any thought or reference. The real number line is overwhelmingly composed of these numbers: the computable numbers, the describable numbers, the numbers you could ever encounter in any calculation or measurement are a measure. Zero dust scattered across a vast, dark continent of numbers that no mind and no machine could ever reach. I spent 3 hours, one night, trying to wrap my head around this, reading Chaitin, and then reading rebuttals, and then reading Chaitin again. And what I kept coming back to is this: we have built the entirety of modern science on an object that is, in the most precise mathematical sense, mostly invisible to us. The number line is dark, not in the colloquial sense, in the technical sense. Almost all of it is beyond the reach of computation, language, and description. There is another layer to the uncomputability result that I think deserves its own space, because it connects directly to the question the entire script is building toward. Consider what it means for a number to be uncomputable. It means there is no algorithm, no finite procedure, no program you could write in any programming language that would output its digits one by one. It is not that the program would take too long. It is not that the program would require too much memory. It is that no such program exists. Not in Python, not in C, not in any language, not in any language that could ever be invented. The numbers digits are, each one individually, well defined. Each one is either a 0 or a 1 in binary, or a digit from 0 to 9 in decimal. Each one is a perfectly determinate mathematical fact. But no finite process can determine them. Chaitin's omega takes this further. Not only is omega uncomputable, but for any consistent formal axiomatic system, there exists a constant n such that no bit of omega beyond the nth can be proved within that system. Different axiomatic systems can determine different initial segments of omega, but every system hits a wall. And the wall is not a practical limitation, it is a logical one. Adding more axioms pushes the wall further out, but never eliminates it. There is always more of omega that lies beyond the reach of your axioms, no matter how many axioms you add. This is Gödel's incompleteness theorem in a different dress. Every formal system has blind spots, and the real number line is composed almost entirely of numbers that live in those blind spots. Let me try to make this tangible with a thought experiment. Imagine the real number line as a vast landscape like a continent. The numbers you know, the ones you can write down, compute, define, describe, are like the cities on that continent. Pi is a city. The square root of 2 is a city. Euler's number E is a city. Every rational number is a city. Every computable number, every number with a formula or an algorithm that generates its digits, is a city. These cities are scattered across the landscape in great profusion. There are infinitely many of them. Between any two cities, there is always another city. The landscape seems crowded with them. But the cities, all of them together, cover 0% of the continent. Not approximately 0, exactly 0. The continent is overwhelmingly wilderness. Not just unexplored wilderness, but unexplorable wilderness. Wilderness that no map could chart, because there are not enough maps. Every possible map you could draw, in every possible language, using every possible notation, describes at most a countable collection of points, and the continent is uncountable. Almost all of it lies permanently beyond the reach of any description. You live in one of the cities. You go about your daily business using numbers that have names, algorithms that terminate, equations that have solutions. You never encounter the wilderness directly. Every measurement you make, every calculation you perform, every experiment you run, produces a number that lives in a city. The wilderness is invisible to you, but it is there, and it constitutes almost all of mathematical reality. That is the number line. That is the object underneath calculus, underneath physics, underneath the decimal expansion of every measurement ever taken. And its most basic structural question, how much wilderness there is compared to the number of cities, is the continuum hypothesis, which we have proved we cannot answer. I want to connect this back to Hippasus, because the rhyme across 25 centuries is too precise to ignore. Hippasus discovered a single number, the square root of 2, that did not fit the Pythagorean framework. The Pythagoreans treated it as a flaw, an anomaly, a thing that should not exist and could be suppressed. What the last 2 centuries of mathematics have revealed is that the square root of 2 was not the anomaly. It was the first emissary from the wilderness. The first signal that the number line contains far more than what our systems can capture. And the wilderness has turned out to be not just large, but overwhelming. Not just hard to map, but provably unmappable. Not just unknown, but, in a formal sense, unknowable. The Pythagoreans were right about one thing. The number was dangerous, not because it threatened their politics or their religion, though it did both. It was dangerous because it was the first evidence that reality outstrips our ability to describe it, that the mathematical universe contains structures that no language, no logic, no axiom system can fully contain. And 25 centuries of progress have only confirmed that initial finding, at deeper and deeper levels, with wider and wider implications. This is where the constructivist challenge becomes impossible to ignore. L.E.J. Brouwer, the Dutch mathematician who founded Intuitionism, argued that if you cannot construct a mathematical object step by step, if you cannot exhibit it, then it does not exist. Mathematics for Brouwer was a creation of the human mind, rooted in a pure intuition of time. He rejected the law of excluded middle for infinite sets. A proposition about infinity is not simply true or false. It is true if you can prove it, false if you can disprove it, and neither until you do one or the other. Hilbert's response, taking the principle of the excluded middle from the mathematician, is the same as prohibiting the boxer the use of his fists. Brouwer was a brilliant mathematician in his own right, a pioneer of topology who proved the famous fixed point theorem. He worked at the University of Amsterdam from 1909, but his philosophical stance was treated as heresy by the mainstream. In 1928, Hilbert engineered his removal from the editorial board of Mathematische Annalen in what the Stanford Encyclopedia of Philosophy describes as an unlawful action. Einstein, also a board member, refused to support Hilbert and left the board. The historian Dirk van Dalen called this the War of the Frogs and Mice. Brouwer was left mentally broken and isolated. He died December 2nd, 1966, at age 85, struck by a vehicle crossing the street in front of his house in Blaricum, Netherlands. In 1921, something remarkable happened. Herman Weyl, who had been Hilbert's star student at Göttingen and was widely considered one of the most brilliant mathematicians of his generation, defected to Brouwer's side. He published a paper titled On the New Foundational Crisis of Mathematics, in which he wrote, "So I now abandon my own attempt and join Brouwer." The paper was electrifying. If Weyl, Hilbert's own protégé, was publicly siding with the Intuitionists, the movement was no longer a fringe position. It was a serious challenge. Hilbert responded the following year with a paper defending classical mathematics and formalism. The battle lines were drawn. On one side, Hilbert and the formalists, who believed mathematics was a system of symbolic manipulations that could be proved consistent by finitary methods. On the other, Brouwer and the Intuitionists, who believed mathematics was a mental construction and that proofs asserting the existence of objects without constructing them were meaningless. Weyl stood somewhere in the middle, gravitating toward Brouwer's philosophy, but unable to fully abandon the power of classical methods. The stakes were enormous. If Brouwer was right, vast swaths of classical mathematics, including most of analysis, much of set theory, and significant portions of algebra, would have to be discarded or rebuilt on constructive foundations. Theorems proved using the law of excluded middle or the axiom of choice, meaning theorems that say something exists without providing any method of finding it, would be invalidated. The mathematical community overwhelmingly sided with Hilbert, not because they had refuted Brouwer's philosophical arguments, which were serious, but because abandoning classical methods would have meant abandoning most of the mathematics they used every day. This is the pattern again. the same pattern that started with the Pythagoreans. When the evidence threatens the framework, the response is not to fix the framework, it is to suppress the evidence. Brouwer's philosophical objections were never answered. They were overcome by institutional power. Hilbert had more prestige, more influence, more allies. He used that power to marginalize Brouwer professionally. The mathematics continued as before, using non-constructive methods, accepting the axiom of choice, treating the law of excluded middle as sacrosanct. But the philosophical question Brouwer raised, whether non-constructive proofs genuinely establish the existence of mathematical objects, has never been resolved. It sits there, ignored but unrefuted, another open wound in the foundations. The axiom of choice, which the mainstream adopted and Brouwer rejected, produces consequences that are genuinely bizarre. In 1924, Stefan Banach and Alfred Tarski proved that a solid ball in three-dimensional space can be decomposed into 5 pieces and reassembled using only rotations and translations into 2 balls identical to the original, 2 from 1. The pieces are non-measurable sets with no defined volume, things the axiom of choice guarantees exist, but that cannot be physically constructed because a real ball is made of finitely many atoms. Ronald Diaconescu proved in 1975 that the axiom of choice implies the law of excluded middle, making it fundamentally incompatible with constructivism. So the axiom that enables modern mathematics to function requires you to accept the existence of objects that cannot be constructed, measured, or described. The question that keeps me up at night, and I mean that literally, is this: does any of this matter for physics? Every equation in general relativity assumes space-time is a smooth manifold, a continuum. The Einstein field equations relate the curvature of space-time to the distribution of matter and energy, and they assume at every point that space and time are described by real numbers, continuous, infinitely divisible. The Schrödinger equation does the same. Maxwell's equations. Quantum field theory integrates over continuous fields. Every prediction in modern physics, from the orbit of Mercury to the energy levels of hydrogen to the expansion rate of the universe, is computed using the real number line as its foundation. But does the continuum physically exist? Loop quantum gravity, developed primarily by Carlo Rovelli and Lee Smolin, predicts that space and time are discrete at the Planck scale, approximately 1.6 times 10 to the minus 35 meters. Space is made of quantized units, and time advances in discrete ticks roughly 1 Planck time apart, about 5.4 times 10 to the minus 44 seconds. Causal set theory proposes a fundamental minimum grain size for spacetime. The holographic principle, arising from black hole thermodynamics, suggests an information capacity of 1 bit per Planck area, not the infinite information density a true continuum would imply. Max Tegmark of MIT went furthest. His mathematical universe hypothesis proposes that physical reality is a mathematical structure. His computable universe hypothesis narrows this further. Only computable mathematical structures exist. If Tegmark is right, the uncomputable numbers making up almost all of the real number line have no physical counterpart. The continuum is a mathematical fiction, an extraordinarily productive fiction that has generated the most accurate predictions in the history of science. Quantum electrodynamics, built on the continuum, matches experiment to 11 decimal places. You do not abandon a framework that works like that. But there is a difference between using a tool and understanding it. The current state of the continuum problem is this. W. Hugh Woodin, the Harvard set theorist, initially argued in 2001 that the continuum hypothesis is false, developing omega logic and the star axiom, which implies the continuum equals Aleph 2. From 2010 onward, Woodin reversed his position, arguing through his Ultimate L program that the continuum hypothesis might be true. The leading figure in the field has argued both sides within a single career. Saharon Scheller holds that many possible set theories exist, and CH holds in some, fails in others. Joel David Hampkins advocates a multiverse view. Solomon Pfefferman argued CH has no truth value. Cohen himself was a formalist who viewed his own result as settling the question by showing it has no single answer. You would think someone would have said something. You would think the fact that we do not know what the number line is, that we have proved our axioms cannot determine its most basic properties, would be front page news. It is not. It is discussed in specialized journals by a community small enough to fit in a seminar room. The engineers and physicists who use the real number line every day have mostly never heard of the continuum hypothesis, let alone its independence. The tools work. The predictions match experiment. Nobody asks what the tools are made of. 2,500 years ago, in a Greek courtyard in southern Italy, someone drew a square and measured its diagonal and discovered a number that could not be spoken. The Pythagoreans called it alogos, without word, without ratio. They tried to suppress it. They may have killed the man who found it, and they failed. The number was real. The crisis it revealed was real, and every attempt to resolve that crisis across 25 centuries has only made it deeper. Eudoxus patched the theory of proportions, but Dedekind showed the patch papered over an abyss of gaps. Cantor mapped the abyss and found it was larger than the thing it was supposed to be a gap in. Gödel and Cohen proved the abyss has no bottom, or at least that our tools cannot find one. Chaitin proved that almost all of the abyss is inaccessible to any tool we could ever build. And the physicists who build satellites and particle accelerators and nuclear reactors on the assumption that the number line is smooth and continuous and well-behaved have never once had that assumption fail. And this brings us back, finally, to the square, the unit square that started everything. Sides of length 1, diagonal of length square root of 2. The simplest possible object containing the simplest possible irrational number. Here is something I have never seen anyone point out, and I think it is worth saying. The Pythagorean theorem itself, the theorem that bears their name, the theorem they were most proud of, is the thing that destroys their worldview. You cannot discover the irrationality of the square root of 2 without first knowing that the diagonal of a unit square has length equal to the square root of 2. And you cannot know that without the Pythagorean theorem. The Pythagoreans built the weapon that killed their philosophy. Their greatest achievement contained the seed of their undoing. Every time a student learns the Pythagorean theorem in a geometry class, they are handling the same tool that shattered the first mathematical civilization. They just do not know it yet. And in a broader sense, this is the pattern of the entire story. Every advance in understanding the number line has produced a deeper crisis. Eudoxus resolved the Greek crisis of incommensurability, but his method deferred the question of what irrational numbers are for 2,000 years. Dedekind answered that question, but his answer defined irrationals as gaps, making the number line a thing composed mostly of absences. Cantor proved the absences are a larger infinity than the presences, but his continuum hypothesis remained unproved. Gödel and Cohen proved the hypothesis is unprovable, but their result left open the question of whether mathematics is complete enough to describe its own foundations. And Chaitin proved it is not, that almost all of the number line is beyond the reach of any formal system. Each resolution opens a deeper problem. Each answer reveals a worse question. The history of the continuum is not a history of progress toward understanding. It is a history of retreating horizons, where every step forward reveals that the destination is further away than you thought. The calculations work. The bridges stand, the satellites orbit, the predictions match reality to 11 decimal places. And underneath all of it, beneath every equation and every measurement and every bridge that stands and every satellite that orbits, there is a number line we do not understand. A number line we have proved our axioms cannot characterize. A number line whose contents are overwhelmingly invisible to computation and language and thought. The real question is not whether the continuum hypothesis is true or false. The real question is whether the real number line, the continuum itself, is something that exists in the way we think it does. Whether it is a feature of reality or an artifact of our notation. Whether the smooth, unbroken line we draw with a pencil corresponds to anything in the actual fabric of space and time, or whether it is a 2,500-year-old idealization that happens to work despite being, at bottom, something we have never understood. 2,500 years after a man drowned for discovering that a square's diagonal cannot be written as a fraction, we still do not know what numbers are. And we have proved, formally and irrevocably, that we may never know.